All right, welcome everybody. Let's continue through chapter 3. We're at 3.3, and here we're going to talk about the basics of z-scores, percentiles, quartiles, and box plots. Yeah, okay, so for the first part, there will be some notes, so be patient as we go through the notes for z-scores, and then we'll do a quick little example at the end, and it shouldn't be too bad to understand this idea of z-score, but don't continue this chapter unless you feel good with standard deviation 3.2, because you have to be comfortable with the idea of standard deviation to really understand this idea of z-scores. So the idea of a z-score is, or a standard score, a standard value, is the number of standard deviations that a given value x is above or below the mean. Yeah? So the z-score is calculated by using one of the following. Notice how we have a formula for population and a formula for sample. And notice that here we're going to say for a z-score for population, we're going to say x. So this is our big X minus the mean, mu. So this is the population mean divided by the population standard deviation. Yeah, wait, sorry, I realize that the pink handwriting is a little off. Okay, that's probably a little better. Here, and for sample, notice how we're consistent with our symbols. We have x minus x bar, so the sample mean divided by the sample standard deviation. So what's the idea between a z-score? All right, let me zoom out. Here, let's imagine that the class takes an exam and the mean is an 80. So student A gets let's say the mean is an 80, right? So everybody takes the exam and you gather all the students and then you take their scores and divide it by how many students there are, and the mean is an 80. And student A gets a 90. So if we just do this where we try and just calculate the score of 90 minus the mean, and we get 10, this 10 implies how far student A is from the mean. This isn't as useful to just stop there with that subtraction, because if I have different populations with different means and different standard deviations, which means a different spread among the data, then it is not very helpful just to know how far ahead of the mean I am. I also need to take into account how spread the data is. Okay? So here, in the previous example, just if you're student A, you get a 90, and the mean is an 80, you're 10 points above the mean. But it doesn't take into context depending on how well the whole class did. And that's the idea with the z-score. So this z-score implies how far away from the mean the data is. Dividing by the standard deviation tells me how many standard deviations I am from the mean. So let's say s is equal to 5. Thus, x minus x bar, we have 90 minus 80. And notice that if we divide it by 5, we have 10 over 5, which is 2. Thus, I am 2 standard deviations from the mean. So let me show you a visual of what I'm talking about, because even though I'm saying it in my own head right now, I could tell maybe there could be a little bit of confusion. So just the idea is, if we have this z equals x minus x bar over s, and we have x is equal to 90, which is the class score, x bar, which is 80, which is the mean average for the class, and s equals 5, which is the standard deviation. If we have z equals 90 minus 80 over 5, we get 10 over 2, which is 10 over 5, which is equal to 2. Now, what does this z equals 2 represent? Okay, visually, you just have to understand that if this is our distribution within the class, let's say, notice how this is the center, right? This is 80. 80 represents the mean for the class. A student gets a 90. How far is that student from the center of the value? You see, this value of 90, you see, notice how this is, your z-score is 0 here, right? The center is always 0, right? And then you have 1 standard deviation, 2 standard deviations, 3 standard deviations. Notice how this represents 80. And each standard deviation is 5. So if this is 1 standard deviation, this is 85. If this is 2 standard deviations, this is 90. If I'm -1 or 1 to the left, then maybe a student didn't do so well. They got below the mean. The idea is this person who got a 90, where are they over here within the normal distribution of the class? They are right over here. This person had a score that was 2 standard deviations above from the mean. Okay? We'll go through some more examples with this idea. Right? But this is just a visual representation of what on earth I was talking about over here. Okay. So Z-score basically tells you how many standard deviations a data point is from the mean. This person is our data point. How far is this value of 90 away from the mean? Notice that this 90 is 2 standard deviations from the mean. Okay, we'll do more examples to get a better feel. Let's take a look at this part over here. Using Z-scores to identify significant values. So notice that using this example here, what I want you to do is just draw this visual, right? Notice that, for example, here, this is -1, this is -2. Imagine if you're a student in the class, right? And you score somewhere over here. This means you scored, below the mean, maybe you scored above the mean. But what about the students who scored above a 90 or below a 70? The idea is if there are 2 standard deviations more to the right or more than 2 standard deviations from the left, then these are significant values. Like if somebody scores like a 90 and above, this is, I guess, considered an outlier, right? So the idea is you're farther away from the mean, right? If you're more than 2 standard deviations, we're going to say this is significantly high value. If you're below 2 standards from the mean, then this is a significant low value. I realize that this should be a negative value. Sorry. Okay. And yeah, a Z-score is a measure of position in the sense that it describes the location of a value in terms of the standard deviations relative to the mean. Okay. This takes a lot to sink in. Okay, so this might take a few days or a few lessons to really get. Okay, so please have this down and try and reread it because this is a really important idea to understand. Okay, let's take a look at an example. Here, which of the following, and take a second, pause the video and copy this down, right? Which of the following data values is more extreme relative to the data set from which it came from? So let's imagine we're asking which is more extreme here. A baby weighing 4,000 grams, where you have where the mean is 3,152 grams and the standard deviation is 693.4 grams, or an adult having a temperature of 99 degrees, where the mean is 98.20 degrees Fahrenheit and the standard deviation is 0.62 degrees Fahrenheit, or a student scoring 630 on the math section of the SATs, where the mean is 500 and the standard deviation is 150. Which is more extreme? The idea is you want to take the Z value for each one of these examples. Okay? So using our formula that we have over here, calculate the Z value for each example below. Okay? Pause the video and try and do that. All right? And let's say you pause the video and you want to see your solutions. The idea is look at the first one here. For the first example, the baby weighing 4,000 grams and the mean is 3,152. We divide it by the standard deviation. This is your Z-score of 1.22. Similarly, for the next example, for the adult temperature with the 99, subtracted from the mean and divided by the standard deviation, and we get a Z value of 1.29. And here we get a Z value of 0.867. So which is more extreme relative to the mean? And it will be this one because it has the higher Z-score. It's farther away from the mean. So let's create a visual, because just showing these numbers is not enough. A visual always helps. So let's take a look over here. If we look at the first example, what was the z-score? We had a z-score of 1.22. This z-score was 1.29, and this z-score was 0.867. Okay? Which one was more extreme? Let me zoom in a little bit. Let me fix the camera angle. Okay. Notice that which one was more extreme? Where this baby weighing 4,000 grams, if the mean is 4,000 grams, right? I'm sorry. If the mean was 3,152 grams, right? If the baby weighs 4,000 grams, right? Where is that baby within this visual? The baby is somewhere over at 1.22. So if this is 1 and this is 2, 1.22 is somewhere here. And notice that they are this much above the mean. What about this example here? 1.29 will be a little bit above the 1.22, so it'll be somewhere over here, and this is 1.29. Okay, and this one over here at 0.867, this is a little bit below 1, so we're over here. Notice that within these three examples, which one of these examples is farther away from the mean? It'll be example 2 with the adult at 99 degrees Fahrenheit. And that's that idea that we had over here, where we're talking about significant values, which is farther away from the mean, and that's this example over here. Okay? Let's go through one more example, and I think this will feel a little bit better. Let me see. It is... Let me just do one little thing over here. Okay. So let me fix this. Let me cover up the solution. Okay. Take a second and copy this down. Right. Person A scored an 87 on their statistic test, and the class average. Oh no! Why am I saying average? The class mean is an 80 with a standard deviation of 5. Person B scored an 82 on their exam, and the class mean was a 73 with a standard deviation of 6. So imagine two different students, right? Let's say we have student A and student B, and student A took a test and their score. Now notice that how do we translate these values over here? I'm sorry, how do we translate what is said over here into mathematical notation that we can understand? Okay, so let's take a second. So student A scored an 87, right? So notice that X is their data value of 87. And the class mean is an 80. So how can you translate the class mean as an 80 into a mathematical notation? Right? Class mean, this is our data value, this is the class mean, and the standard deviation is 5. Okay. What about the next one? Student B scored an 82. Okay, so we got to draw somebody, right? Oh god, this person looks a little bit better than this one. I gotta fix this. Okay, so here this is a data value of 82, and the class mean was a 73, and the standard deviation was a 6. So imagine two different students take two different exams and two different classes, right? In one class, the mean was an 80 with a standard deviation of a 5. In the other class, the mean was a 73 with a standard deviation of 6. Notice that this student scored higher on their exam, but the mean was an 80. And this person scored an 82, but here the mean was a 73. The idea is I did not want to show you that. Who scored better with respect to their class? Okay, now don't rewind and pause and see what I wrote. What I want you to do is take your time. Who scored better with respect to their class, right? How would you solve this question? The idea is, if you pause the video and you want a little hint, get the z value for each one of these students. What is the z-score for this student's exam within their class, and what's the z-score for this student? So if you wanted to try and find the z-score for each one, it's just like this. Here with student A, right? This was their score. This was the mean subtracted by divided by the standard deviation of 5. And notice you have 7 over 5, which is equal to 1.4. And student B, their z-score was 1.5. So for A, you had 1.4 and 1.5. So who scored better with respect to their class? It would be student B. Even though they got a lower score than this student did better with respect to their class, because if I were to show some sort of normal distribution, right, for each one of these students, notice here, what is the mean over here? The mean is that this is 0, and this is 1, and this is 0, and this is 1. 1.4 is maybe, this is 1.4. My bad, let me zoom in a little bit. This is 1.4, and this is 1.5. Notice 1.5 is farther to the right from the mean than 1.4 is. So this student B did better on their exam with respect to the class than student A. And that's the idea of a z-score. Okay. I hope you enjoyed this video. If you have questions, let me know, and I will respond. Enjoy.